Hey everyone, it's Emily. This video is all about the Chi-Squared Statistic, how to calculate it by hand, how to make sense of the test statistics results, and I'm going to walk you through some practice problems about Tiger King. Let's get started. Chi-squared is a non-parametric distribution, and we're going to be using it to understand whether two variables are statistically independent of one another. Before I go any further, chi is how we say this word. Chi is a Greek letter. It's written as a funky long X like this. Again, it's a non-parametric distribution, so non-parametric tests require no assumptions about the distribution of the dependent variable. So our hypotheses do not refer to specific population parameters, and we don't have to worry about whether our data is normally distributed or not. Something you should know, when we work with non-parametric tests, it's kind of hard to pass these tests mathematically, so you're less likely to find significant effects or differences in non-parametric tests. It's a little challenging to explain this mathematically. However, if you pass this test, you're less likely that passing this test was a false positive. So if you get a positive result for this test, you can be pretty confident that there's something going on. So yes, the chi-squared test that we're going to be learning about in this video is an example of a non-parametric test. Before we review the test, let's look at what the chi-squared distribution looks like. And it's another one of those distributions that changes based on the degrees of freedom that are associated with your test. So as you can see, here's an illustration of what the chi-squared distribution looks like when the degrees of freedom are only 2. See how it has this asymptotic relationship with the y-axis and the x-axis? However, as we increase the degrees of freedom, here it's increased to 24, you can see that this tail that used to hug that y-axis now hugs the x-axis. So the shape of this distribution shifts as you increase the degrees of freedom. As we continue to increase the degrees of freedom from here at 24 to about 90, you will see that it better and better approximates the normal distribution. So here you can see we do have a skewed right, when the degrees of freedom are about 24, but you can see emerging is this normal distribution shape. And as we keep increasing those degrees of freedom, this skew will reduce and it will become more and more symmetrical. The chi-squared distribution is what we use for our test of independent statistic. So just to know, and this is a good way to check your math, your test statistic that you produce using this test is always going to be greater than or equal to 0. The mean of the distribution is located to the right of the peak of the distribution, which makes sense because we see that chi-squared is skewed to the right. Like many previous tests that we've done in this class, statistics courses have taught that significance determination is going to be using a critical chi-square value. Usually you get that from a special table or some other means. We're going to use another app produced by Matt Bognar to find our test statistic and see if it's statistically significant. And remember, we're going to denote our test statistic by writing chi-squared. All right, I know that this formula is intimidating, but we're going to walk through it piece by piece. I don't want you to feel too scared by this. Once you realize that this is a methodical procedure and it's pretty easy to visualize, I think you're going to like this test. In fact, students have reported that this is one of their favorite things to learn and do in a course because even though it's a little tedious, it's very easy to visually understand what's happening and to produce the correct result every time. So again, the chi-squared distribution is what we use for our test of independent statistic. Essentially what that means is that you're testing two groups and you're seeing if they differ on some outcome variable based on the difference between expected and observed values. Let me clarify what we mean by expected. We're talking about mathematical expectations. This isn't what you personally expect, or even what social science theory tells us to expect based on previous research. Expected is a value that we calculate for each cell in a contingency table. Observed values are the values from the raw data. So whether or not theory or mathematical expectations tell us that we should have a different value, the observed values are what is present in the data set. Here is the formula for the chi-squared test. On the next slide, we'll walk through this piece by piece. First, let's look at each piece of this formula, and then I will break down in words what's happening in narrative form. This is the chi-squared symbol. See that long and funky X, and then a superscript of a 2? That's chi-squared. It's equal to, here is the symbol for sum. It's the mathematical symbol for sum. That's telling us we're going to add up a lot of fractions that are constructed this way. First, we take the observed value of one cell. We subtract that expected value from the observed value. We square that difference, and then we divide that squared difference by the expected mathematical value for that cell. We do this for as many cells as there are in our contingency table. We add them up. So again, what is this telling us? Our test statistic is equal to the sum of this fraction for each and every cell that contains data in your contingency table. Observed values minus expected values, squaring that difference, and then dividing by your expected value. Here's what chi-squared looks like in Stata. I enter the tab or tabulate command, and then I enter two variables that I want to enter into a contingency table. Here, my first variable is active participation in a political association. So active1 is the variable name in my data, and I want to see if that varies by country or region. That variable is stored under N country in my data set. So as you can see, at the intersection of each country or region and response to active participation in political association, we have a frequency in this top section of each cell. I should clarify, Stata doesn't put in columns, but if I did, it would look like this. Now it's probably easier to see that each of these cells that exists has in the top a frequency. These are observed values. It's not what we expect. It's not what we think should happen. It's just the raw data that's given by the data set of everybody who is from China and is actively involved in a political association. So let's look at another intersection. Folks from South Korea who are hardly involved, but yes, involved in a political association. We look at that top value. That means that 48 people in this entire data set were both from South Korea and, yes, but hardly involved in a political association. Now for the second value, Stata actually reports a percentage here in the lower section of each cell. So for example here, 5.73% of all of our respondents were from China and, yes, actively involved in a political association. So here in this box, you can see that 2.43% of all the folks that responded to this survey were from China and were, yes, but hardly involved in a political association. Let's talk about the difference between total rows and columns and the data rows and columns. If you wanted to see N, your total number of respondents in your sample, you would want to look at the total cell here. There are 9,965 folks that responded to this survey. Here are the totals for each of these rows added up. 285 plus 26 plus 14 plus 9 is 334. So regardless of country or region, 334 folks said yes, they are actively involved in a political association. Similarly, if we go down each column, this total represents adding everybody together who responded who was from China. 285 folks plus 121 folks plus 4,565 folks equals this total. All the people who responded who were from China, 4,971 folks. When we're doing calculations, you need to remember that there is a difference between the total row and total column and the actual data at the intersection of each possible variable. So when I'm working with this calculation by hand, what really matters are the cells that I've circled below. When I've excluded the total column and the total row, and I've focused on this center portion, I can see that there are 12 different cells because we have 4 columns and 3 rows excluding the total column and row. That means when I calculate my chi-square statistic by hand, I'm going to be creating one of those fractions for each one of these cells. So I'll be adding together 12 different fractions. Thankfully for this example, Stata has done the work for us, and it's given us this result. It tells us that Pearson's chi-squared statistic is equal to 206.3631, and the probability is less than 0.05. It's really significant. So what it's telling us is that yes, there is a relationship between country and region and whether somebody actively participates in a political association or not. Here's an example that I did with a previous section of this course in person. I wanted to see if there was some kind of association between whether you were a cat or a dog person and whether you were a coffee or tea person. Of course, this is silly. This probably really doesn't matter in our social lives, but it was an easy example to ask everybody quickly about their preferences. Do you think that there is some kind of association that people who like dogs also like coffee, or people who like tea like cats, or a different combination of variables? We wanted to find out. So I asked everybody in the class and then tallied up our information. I had these observed values that I wrote here in the top of each cell. So there was one person who was a cat person and preferred coffee. There was one person who was a cat person and preferred tea. And there was one person who preferred another beverage but was a cat person. See how this works? There were 13 people who were dog folks who preferred coffee, 5 folks who preferred tea and who were dog people and preferred tea, and then 4 folks who were dog people who preferred another beverage. And then finally, we did the same thing with this final row. One person liked coffee, but not pets. One person liked tea, but not pets. And one person liked another beverage and did not like pets. See how this works? So I just want to clarify, these whole numbers at the top of the cell are the observed values. Our next step was to create total columns and rows. And this is as simple as adding together across each row and column. 1 plus 1 is 2. 13 plus 5 plus 4 is 22. 1 plus 1 plus 1 is 3. See how this works? So we generated a total row. We did the same thing going down with our data, and then we found our total, which is the number of all of our respondents for this question. Next, we calculated our expected values. This is required for each cell, and it's pretty easy to do by hand. You need to create a fraction for each cell. You find the total at the end of the row of that cell you're interested in. You multiply it by the total of the column that you're interested in, and then you divide it by the total n. That's 1.1, and that's the expected mathematical value for this cell. So here we go to the end of the row, 2 times 7, the end of the column, divided by 27, that's 0.52. And we repeated that for all of this. That's the first key step in completing your chi-square statistic. I want to walk you through the worksheet that we've created for the course so that you can know step by step how to complete your chi-square test. Then we'll go through the Tiger King example problem as promised. So let's do a review of what the scenario is behind a chi-squared test. The scenario is you have a contingency table, good vocabulary word, with 2 variables. One represents the rows, one represents the columns, and each cell contains the frequency observed at each of the intersections between those rows and columns. For the purposes of this class, we will assume that each category in your table is mutually exclusive, that there is no overlap. In other words, each person or item in your data set could only pick one of the columns and one of the rows to belong in. We're going to also assume that the frequencies were observed by random sampling. You can perform this test to look for an association between 2 variables that are not continuous in nature. There are no statistical assumptions that we are making about the sampling distributions. It doesn't have to be normally distributed. Do you remember why? Exactly. Chi-squared is a non-parametric distribution, so we don't have to worry about distribution assumptions. Here's the big question, the whole point of why you want to complete this test. You want to see if there's a statistically significant difference between the expected frequencies for your variables and the observed frequencies for your variables. In other words, if we gathered up all of the observed frequencies and we redistributed them mathematically as evenly as possible, would there be a statistically significant difference? Outcomes of the test. If your data pass this test, you could say that there is an association between those two variables that goes beyond random chance, or that your variables are correlated or linked. If there isn't, you could say that the variables are independent of one another, that one variable doesn't depend on the other. You can't, however, determine causation. So we can say that there is a link or a relationship or interdependence of these variables. However, you can't determine which one causes the other, or even if there's any causation at all between your two variables. Step 1 of the problem, as itemized on your worksheet, is to identify and organize the details of your problem, and you want to calculate totals where and if necessary. So make sure you identify the two separate variables you're testing, your rows and your columns. Now look at this. This is an example problem, and it's willingness to use, and in this case, it's willingness to use a medication. And then you have males and females as the labels for your rows. So for our rows, we could write gender, and for our columns, we could talk about willingness to use. You're ensuring that your data are organized in this frequency table that we call a contingency table, as exemplified below, right? So we have all of our data at intersections between columns and rows. Now take a look at this table. Do we have a total row or column? If you don't, you want to create those and calculate the totals. What we would do is create the total row and the total column by simply adding across each row and each column to produce that information. So here I've done this for you below. 17 plus 32 plus 11 is 60. 13 plus 43 plus 34 is 90. 17 plus 13 is 30. 32 plus 43 is 75. 11 plus 34 is 45. Now, here's a good trick to check your math. You can generate the total, or your n, by going either way. You can calculate down, adding 60 plus 90 is 150. And you can make sure your math is correct by adding across your row of your total row. 30 plus 75 plus 45 is also 150. That's your total n for this problem. Of course, a final way to triple check your math would be to add up by hand each of the values in your data cells. Now let's calculate the degrees of freedom, which you know is often written as df. For these problems, we calculate degrees of freedom as follows. We take the number of rows containing original data, not our total row, but we take the number of rows containing data and subtract 1, and we multiply it by the number of columns including that original data, and we subtract 1. So in this case, remember, we're not including the total column or the total row. We're instead just focusing on the original data portion. So how many rows do we have? 1, 2. So we have 2 minus 1. How many columns do we have? 3 with original data, so 3 minus 1. 1, 2 minus 1 is 1, times 3 minus 1 is 2, is 2. So our degrees of freedom for this problem are 2. Finally, we're going to set the alpha level. Since we haven't been given any other specific direction, we're going to set it at 0.05, that scientific standard for significant. The next step for this problem is to clarify your research question and set up your hypotheses. Understand your research question. It's always going to be in this format. Is your rows variable associated with your columns variable? In other words, is gender associated with your willingness to use your medication? That's your research question. For chi-squared tests, we always set up the following mathematical null hypothesis statement. There is no association between gender and willingness to use. And for chi-squared tests, we always set up the following mathematical alternative hypothesis statement. There is some association between gender and a willingness to use medication. Next, you want to compute the expected frequency for each cell. So you have your contingency table here, and you will calculate for each cell by using this simple formula. Start in your first cell. You want to take the row total, which is 60, times the column total, which is 30, and divide that product by your total n. So 60 times 30 divided by 150 is 12. I always write my observed frequencies at the top of the cell and my expected frequencies at the bottom so I can keep organized. So you repeat that process for each of the cells, not your total cells, but each of your cells that contains original data. Step 4 involves calculating the actual test for independence chi-squared statistic. Again, here's your formula. You're going to add up all of these fractions. For each cell, you will take your observed value, subtract your expected value, square that difference, and then divide it by your expected value. So this is what it looks like. Remember on the previous slide we had 6 different cells with data? We go one by one across each row to create these fractions. In the first cell, the observed value was 17, the expected value was 12, so we take that difference, then we square it, and we divide it by the expected frequency. Then we go to the next cell. The next cell had an observed value of 32, an expected value of 30. You take the difference, you square it, and you divide it by the expected value for that cell. And you continue with that fraction until you've done it for each cell. You can simplify those fractions and then add them together, and you get a number that's positive and greater than or equal to 0. The test for independence generates a final answer that then determines your chi-squared distribution. So here, after adding up all of these fractions as the formula tells us, we have a chi-squared value of 8.23. Now we need to see if that's a large enough value to be statistically significant given our degrees of freedom. So in step 5, we're going to use the ChiSquared App, thank you to Matt Bognar, to obtain your alpha level. So here's a link for you to use, bit.ly/B Bognar, capital C, Chi, C-H-I. We're looking for a proportion in one tail because of the shape of the chi-squared distribution. So we're going to select this option that has a greater than sign indicated like this. You're going to enter your degrees of freedom here in the top left or white box where it says degrees of freedom equals. So for our problem, it was 2. You're going to enter your test of independence value in the bottom left or blue box. Click away and the returned value in the bottom right or red box is your alpha level. Here you can see the returned alpha level is less than 0.05, it's about 0.01. Finally, we want to compare the returned alpha level and we want to make a decision about our hypotheses. What we're doing in essence is that we're determining whether we can say that for your degrees of freedom, the test of independence value you calculated generates an alpha in the chi-squared distribution that is less than what is necessary to determine that the groups are correlated with statistical significance. Your mathematical question is simpler. Is the alpha value returned from the ChiSquared app less than or maybe equal to 0.05? If you were specifically asked to test an alpha level lower than 0.05, like 0.01, you guys are pros, you know what to do. You just want to see if your returned value is less than or equal to that value. So if yes, the returned alpha value from your chi-squared app is less than what it needs to be, the null hypothesis can be rejected and you accept the alternative. So your final answer would be that yes, there is an association between your rows variable, remember it was gender, and your columns variable, remember it was willingness to use a medication. And you include this statement at an alpha level of p equals less than 0.05. If you were again, and obviously you would change this number if you were specifically asked to test at an alpha level lower than 0.05. Just change that last part of the sentence. So if no, the alternative hypothesis should be rejected. you accept the null. Your final answer would be that there is no association between gender, which was our rows variable, and our columns variable, which was willingness to use medication. As a reminder, can we determine causality such that gender causes your willingness to use a medication, or in a physically impossible case, that somehow your willingness to use a medication causes your gender? Absolutely not. We cannot determine causality using this test. We can only use relationship between, or association between, or a correlation between two variables, but definitely not that one causes another. All right, let's do another example walkthrough. This time we'll do all the math live for you so that you can see exactly how we're completing this test. So of course we're using fake data, but again, these are dire and challenging times of COVID-19, and I'm sure many of you, like me, have been binging Tiger King, so why not just have a little fun, and we'll pretend that we're looking to see whether there is an association between these big cat folks and what kind of big cats they own. Is there a preference to owning one versus the other? Can we statistically see whether there's an increased likelihood that Joe Exotic or Carol Baskin owns more jaguars than tigers with statistical significance? We'll see. So our question is, how many tigers and jaguars have Carol and Joe Exotic owned in their lifetimes? Is there a statistically significant correlation between these individuals and their big cat preferences? So let's first examine our table. We have a contingency table. Remember that we have one variable on the top, which is big cat type. And we have one variable that generates our row headers. So we have Joe Exotic and Carol Baskin. And at the intersection of each of these rows and columns, we have a number, which is a frequency. These are all observed frequencies. So in this fake example using fake data, Joe Exotic owns 130 jaguars and 1,382 tigers. Carol Baskin owns 87 jaguars and 2,113 tigers. We are given a total column and a total row. However, if you weren't, you know how to calculate them, right? You would say 130 plus 1382 is 1512. You would again add across the row for this cell, add down each column to generate totals here at the bottom, and then you can triple check your total n by adding up the two values in the total column, or adding up the values in the total row, or even just adding together these four original data points. Step 1 in our worksheet for chi-squared test problems is to get organized. So remember, we have to figure out what are the two separate variables you're testing. What are our rows? Our rows are these people that own big cats. Our columns are the different kinds of cats. As I go through this problem, I'm going to call the big cat owners O, and I'm going to call the cats themselves C, just to save myself from scribbling a lot in this problem. Of course, when you're doing a problem and you're writing it out by hand or typing it into your computer, always use the full variable names. I'm just doing it because y'all know my handwriting's bad. Okay, now we're going to calculate and confirm the sample size for the problem. Remember, we can do that 3 ways to check our n, but we're going to go with what's here on the screen. N is 4,412. Now we're going to calculate our degrees of freedom. How many columns do we have? 2. We subtract 1 times. And now how many rows do we have? We have 2. 2 minus 1. So that equals 1 times 1. Our degrees of freedom are simply 1. All right, and we're going to set the alpha level. We weren't given anything, so we're going to go with our standard 0.05. Now let's understand our research question, and it's always formulated this way. Is our rows associated with our columns? Or in other words, is a cat owner associated with owning a specific type of cat? Our null hypothesis is that there is no association between cat owner and specific type of cat, the likelihood of owning specific types of cats. And our alternative hypothesis is that there is some association between cat owner and specific types of cats. Now we're going to compute the expected frequency for each cell. I know that it's tedious, but it's pretty simple to do. Remember, you're using this simple formula for each cell. Take the row total, multiply it by the column total, and then take that product and divide it by your total n. Visually, that looks like going to the end of this row, taking 15, 12, multiplying it by the end of this column, 217, and then dividing that number by here in the corner, 4,412. So if I do this, 1512 times 217 divided by 4412, that's 74. Here, if I take 1512, multiply it by 4195, and then divide it by 4412, that's 1438. Here, if I take 2900, multiply it by 217, and divide it by 4412, I get 143. Last time, if I take 2900, multiply it by 4195, and divide it by 4412, I get 2757. Now, I want to be super clear. I have rounded these to whole numbers. I think it makes a lot more sense for an undergraduate learning how to do this for the first time to round everything to a whole number. It isn't going to be exactly perfect, but it is a really good way to simplify this problem because I know doing this by hand, it can get a little tricky when there are a lot of extra digits that you have to monitor. So when I do this, I round to the nearest whole number. That really helps me with my calculations and simplifying fractions. You can be more specific if you want to be, that's fine, but when we're grading your assignments, we take into account that you probably are going to be rounding your expected frequencies to the whole number place. And we give a little bit of wiggle room for your chi-squared statistic, depending on how you decide to round it. As a reminder, we've only looked at the cells that have original data. We haven't done anything with total columns or rows in terms of calculating a new expected frequency. So my setup is consistent. I have my observed value at the top, my expected value at the bottom of each cell. I've cleaned things up for you on this slide, so everything's typed in. Again, you can see we just have our observed and expected values organized in each cell. Now you're going to calculate that test for independence chi-squared statistic. Remember, you're going to create a fraction for each cell using this formula. Observed value minus expected value, square it, and then divide by the expected value. Then you will add all of those fractions together. How many fractions are you expecting to add together? Well, we exclude the total rows and columns, and we just look at the original data of our problem. We have 4 cells that had original data, excluding totals in rows and columns. So we will be adding together 4 fractions that we create, 1 for each of these cells. So let me write out what this looks like for you. Again, remember, I've rounded everything to a whole number just because those extra digits can really get in the way, and it often doesn't make a big difference for the practice problems that we're doing in terms of generating a chi-squared statistic and in terms of seeing whether it's significant or not. So I encourage you to round. In data or other statistical programs, there won't be any rounding, so you can be sure it's super precise when you work in data. So let's create our first fraction. We're going to take our observed value, which was 130. We're going to subtract our expected mathematical value, which is 74. We're going to square that difference and then divide that value by our expected value, 74. We're going to add that to our next fraction. 1382 is our observed value. We're going to subtract our expected value. We're going to square that, and we're going to divide it by our expected value. 2 more fractions to put together. Here we're looking at Carol Baskin's Jaguars. So we observed that she has 87, but mathematically, we've expected that there would be 143. We're going to square that difference, and we're going to divide it by the expected value. We would have mathematically expected that Carol Baskin had 143 Jaguars. One last fraction. We're going to take the observed value for Carol Baskin's Tigers, which is 2,813. We're going to subtract our expected value. I know it's getting squished. We're going to square that difference, and we're going to divide that by our expected value, 2,757. Phew! All right, so my suggestion for you is to first simplify this information for each fraction. So take 130 minus 74 and square it, and then divide by 74, write that number down. And then complete this fraction, and then write it down so that you have the fraction simplified into decimal form for each of the fractions you've created. I've cleaned it up for you on the next slide. Here I took those exact fractions and I simplified them into decimal form. So I'm saying that the sum of each of the 4 fractions I needed to create to generate my chi-square statistic are 42.38 plus 2.18 plus 21.93 plus 1.14. And that equals a chi-squared statistic of 67.63. Now for step 5, this is when we use the ChiSquared app to obtain our alpha level. So again, here's the link for the app. We're looking for a proportion in one tail because of the shape of the chi-squared distribution, and we need to obtain the alpha level that's equal to this value. So I've entered my degrees of freedom here. It's 1. Remember, this is the shape we expect when our degrees of freedom are low. When they're 1 or 2, we see this shape. We enter our test of independence value, our chi-square statistic here, where it says X in the blue box. So I've entered 67.63 here. And then when I click away, my value that's returned is 0. And you think, is this an error? No, this is just telling us we are super, super significant. It's like saying 0.00000000, which is obviously less than 0.05. So what do? Let's check on the next page. All right, so we are comparing our returned alpha level. Remember, in step 6, in essence, what we're doing is determining whether we can say that for our degrees of freedom, whether the test of independence value we calculated, that's our chi-squared test value, generates an alpha in the chi-squared distribution that is less than what is necessary to determine that the groups are correlated with statistical significance. Phew, I know that's a lot. Mathematically, all it means is that returned alpha level in red, returned from the ChiSquared app, less than 0.05, right? Is 0, the value we got back from our app, less than 0.05? If yes, we're going to reject the null hypothesis and accept the alternative. If no, we're going to reject the alternative hypothesis and accept the null. So which should we do? Yes, 0 is less than 0.05, so the null hypothesis can be rejected, and you are going to accept the alternative. Your final answer is that there is an association between pet owner and the kind of cat that they own at an alpha level of p is less than 0.05. So in other words, there seems to be some kind of relationship between the cat owners Joe Exotic and Carol Baskin and how many cats they own of particular types. In our fake example, it was jaguars and tigers. So our top 3 takeaways from this video, again, they're never comprehensive, but they're just to guide your learning. Remember, the chi-squared distribution is a non-parametric distribution that changes based on the degrees of freedom that you have. 2, I want you to practice with the worksheets and master how to compute chi-squared tests using this equation. 3, I know these are really challenging times. This video is posted during the COVID-19 pandemic. I hope that you all stay well and safe and healthy, and go ahead, binge a little bit of Netflix. Tiger King is a wild ride. Thanks, everybody. Have a good week.